All right.
So the next talk is from Conrad Zimmerman on Latte, lightweight alias tracking for Java.
All right. Hi, I'm Conrad Zimmerman. I'm a student at Brown University, and this is work done with the four of us here. And yeah, today I'm going to talk about a system that we're calling Latte, lightweight alias tracking for Java. And I should say, disclaimer, this is work in progress. I will talk about some of the things as if we had a tool. We do not, in fact, have a tool yet. We have a formalism that we think translates to a tool quite nicely. And yes. So a little bit of motivation here. Why do we want alias tracking? You probably are already convinced that we care about aliasing if you're here. But as a simple example, and sort of to introduce you to the setting that we're concerned with here, we're trying to do lightweight verification, specifically of Java code. And you may have heard of liquid types, made popular by Liquid Haskell. And this is some work that Catarina has done on bringing liquid types to Java. And in Java, we have a lot of mutation. A lot of the talks have talked about code that can mutate objects, and ours is no different. So here we're trying to verify some account transaction system, and so we want to say that the balance that you have to have at least as much money in your account as you want to withdraw. And here we're trying to withdraw from two accounts the same amount simultaneously. And if you're thinking about aliasing, you might already see the problem here. We can't verify this code. Because what happens if A1 and A2 are the same account? You're withdrawing twice from the same account. And this sort of conflicts with what we want to do with liquid types. We want to have a simple way of reasoning about objects in Java where we can just sort of add. Liquid types are supposed to be like just more powerful regular types, right? We want to talk about objects and be able to refine those types to include things about like the value in the object. And here we have to start thinking about other things. And this is sort of by the nature of mutation and how Java handles objects and all of that. Yes, but we want to find a way to actually verify this code easily. And so some goals here that we have as we set out, like I mentioned in the setting of verification and specifically of Java code. First of all, we want sound reasoning. We want to be able to guarantee certain properties about our program. We want few annotations, so we don't want to clutter our code with extra annotations. And also, those annotations and everything that you need to think about should be simple, including the invariants that you have to maintain throughout your program code. Another thing that we want is precise alias tracking, and this is something that will become sort of obvious hopefully as we go along about why exactly we want precise tracking. But intuitively, you can already understand maybe that if we're trying to do a verification versus the data race prevention that we've heard about a lot today, verification requires exact tracking of mutation, or some way to reason about separation, whatever, to track those aliases to be able to guarantee that a certain mutation won't affect another, or another value. And in our system, this is a very important goal that we want to have. We want to have simplicity, and in fact, we value simplicity before expressiveness. So this sort of goes back to the liquid types setting. Liquid types are not meant to like be the be-all, end-all of verification. For that, there's other tools, many other tools, in fact. Liquid types are meant to just start down the path of verification, and in our setting, we are okay with trading some expressiveness, which, what does that look like and everything, we'll get into, and we can discuss that further. And this is also sort of to align with how Java developers think and reason about their programs. We don't want to introduce completely new paradigms and stuff, which goes into our constraints that we're trying to accommodate. The first one is accommodating existing code. We want you to be able to start using liquid types in Java without rewriting your program from the ground up using some other pattern. And we want to produce aliasing information for liquid Java, for other tools, whatever you want. We are focused on the verification setting. There may be other applications of this. So some related work that you are probably somewhat familiar with, at least. Separation logic. This is sort of like the standard approach for verification. Just define some logical constraints, specify your separation, reason about how separate value, like non-interference, etc., for mutation. This is imprecise, though. As I was saying before, you have a group of things that are separate from other things. We can't give nice error messages. Often in separation logic verifiers, debugging a failure of the verifier to prove some specification is quite complicated. And even the notation is quite complicated. As an example, here's an example from the CN language, which is verifying C code with refinement types. And this is a bit different syntax maybe than traditional separation logic, but it does translate to separation logic. And this is a specification of a binary tree. And another big point of this is that we're defining our predicate separately from the class definition that you might have in Java. And for different properties, you'll need different predicates, each with their own separation properties. This gets complex pretty fast. Another related work is ownership types. Again, this is somewhat imprecise. A nice thing about this is that you got to specify the heap structure and some of your invariants on the objects along with the data structure. So that's nice, but this can get somewhat complex. You have to reason about a different ownership graph instead of just the regular reference graph that the developers are normally used to working with. As an example, this has been done for Java, and here's what it might look like. This is extending the map class. There's all sorts of things that you can do as far as inference here and stuff like that I won't get into. And it's very interesting work. The question mark here is not gradual typing, but it's more like inference, but anyway. Another related work that's come up in pretty much all the talks is REST. REST has an ownership system with borrowing, uses immutable values by default. This has been used by verifiers, so we can do it. But it uses vastly different patterns than are commonly used in Java programs. The borrow checker is often very difficult to understand. This is something that you probably know either from using it or from talking to REST developers, but there's been papers and research on that. And it requires additional semantics, changes to the way we run code in order to encapsulate some of the patterns that we use in Java. So another work is alias burying. I'll try to get through this list here since you've probably seen some of these, but the idea here is that if we don't use an alias, it doesn't matter, and so we can just sort of go through our program and reason about it that way. This does, though, break encapsulation, at least the way it was formulated first of all, where you would have to include the access fields in a method. Java developers are not used to that restriction, having the access fields be in the public API. And yeah, attempts to restore this encapsulation use new patterns like effects. So some more recent work, and we've heard even some today. Milano et al. Defined a new language that uses regions. This one is interesting because it did focus on that lightweight aspect and easy to use. However, this did use new language constructs and things like that we don't have in Java. Holler and Loico made La Casa. This requires object capabilities, etc. But this is another interesting lightweight approach. So today we will see how Latte satisfies our set of goals and constraints. So our approach, the idea here is that we enforce uniqueness of references on the heap. The heap is hard to reason about, and so we're going to talk about unique references there. We allow aliasing among local variables when it can be, excuse me, when it can be precisely determined. I need. Okay, so, yeah. We annotate the unique fields and the parameters to specify the uniqueness properties that we want. And we infer the uniqueness and aliasing of local variables. So we do this in a type environment that you'll see shortly. So what annotations do we have? Well, we have 3 of them. We have shared parameters, or shared fields and parameters. These are just the default, what you use in Java every day. In fact, our tool would probably not even require you to specify this. We have unique fields and parameters, so these are values that are unique. In a sense, if you have a unique value, you own that value in terms of like ownership types. This means that the value is not referenced by another field or a non-alias variable. And we have owned parameters. So the syntax here is flipped from in REST. So here we have owned parameters. You borrow an argument whenever you pass it to an owned parameter. This is our idea for this is that you want to talk in terms of the method body. So whenever the method executes, the value is owned by some calling context. So here's an example where we check a stack implementation. Here we are storing unique values in the stack, and this would be so that whenever we verify, we can ensure that no changes to those values occur while they're on the stack. We have a more complete example in our paper. But you'll notice the unique annotations here. And here's an example of a push method for that. So this is hard to read on here. Okay. We have an owned this parameter. So in Java, this is a syntax for annotating the receiver of a method. And we have a unique value. So notably, the value here, whenever you call the push method, is consumed. After you call this, you don't have access to the value anymore. But the receiver is borrowed. So to begin by checking this, to show how our system works a bit, we start off with what you might expect from the declaration of the method. And we start by having some variables, R and N. We assign this.root to R, where we introduce the alias. Here you'll notice we allow aliasing on the stack or in the local environment, like I mentioned before, but we precisely track that in our type environment. And these annotations in the environment are inferred. This is because they actually change during the lifetime of a variable. We don't want to declare something and then have it change later. In the next line, we nullify the root value. This is equivalent to a destructive read. Sometimes you can avoid this with using the local aliasing, as we'll see later, but in this case, we do a destructive read. You could also instantiate a new node with a null next pointer or something like that. Now we create a new node, and we pass it the value and the R. Yes, there we go. And this consumes those 2 values because we can't allow aliasing outside the values that are stored in N on the heap because we treat the constructors as opaque and we don't expose the we don't impose any restrictions on the heap structure after the constructor returns. Again, we set this root to n, and which introduces a new alias that we also precisely track here. And so whenever this finishes, we're left with, from the perspective of the caller, just the unique root value, and no aliases exist. So here are some technical details of how we do this. We remove references to the overwritten environment to an overwritten object in the environment through a process that we call isolation. If an object is alias, we move ownership of that value to some alias that we pick. If there are no aliases, then we can't reference the objects that it contains in any other way. Therefore, we can count those as unique values and transfer ownership to the alias fields, of which there may be multiple. And this allows destructive reads of a parent to disconnect a whole chain of values. So what this might look, this does not have my transitions right, but whatever. Okay, we're showing all four of them at the same time. So if you see in the A block here, we have aliases to root and root.value, and then we nullify this .root, and, okay, yeah. And we are left with the A prime here in the bottom, where we have an alias to r.value. This doesn't actually change the aliasing structure, it just changes how we are tracking that. Before that value, r.value, was also aliased with r.value transitively. But this changes how we annotate it. And then in the right, if we disconnect this .root, but we have no aliases of root, we can assume that the unique values that it contains are, or aliases of the unique values are unique. All right, so here it is in code. We have, the method of this is using the stack, but now we are trying to deck the value at the tail of the stack, so accessing this as a queue. And we start by creating this alias to n.next.value, and then we disconnect n, and we are left with a unique value. Yeah, there's some other interesting things about this method and how isolation works with it, because the caller of this uses one destructive read to disconnect and be able to traverse the entire tree, but you can see that in the example in our paper. So this verifies fine. We're left with a unique value at the end. One other detail about our tool that is fairly important to consider is that it requires all unique or owned parameters to be separately unique. This term comes from a paper from Holler and Odersky. And this is actually a limitation of the expressive power of what we can reason about. So it's an important consideration. And the reasoning behind this is that if you were able to reference a unique or borrowed object from two different paths, we're not able to maintain our aliasing invariants and precisely identify the aliases. And because we have this, we have precise alias tracking, and this allows informative error messages even in this case. So our tool can help the user reason about this more complicated requirement. As a simple example here, suppose we had an add method, takes two values, does something with them, and we want to be able to pass it like a value x and a field of x, like here, or an alias of a field, for example, but we can't because we require them to be separately unique. This is also a problem in Rust, if you're familiar with that pattern. Yeah, we think that because we have precise error messages, this is at least something that we can assist the user in reasoning about, but it is a trade-off here. There's no free lunch. Another thing that I mentioned before is how it consumes values. This is sort of like a linear modality. So if you pass a value to a unique parameter, it becomes inaccessible. This also enforces separate uniqueness of unique values. We don't even have to check that. We only have to check that with borrowing, or check it explicitly, I should say, whenever you borrow. Because if it becomes inaccessible, you can't access it later. And here's a simple example of why you might want to consume a value. For this example, it's message passing. Suppose you had some actor that's running on maybe a different thread. You want to send it a message. You send it a message, and you try to then modify the message afterwards. It errors because it's not accessible. And these simple annotations allow you to enforce this invariant. So you could do, for example, copy-free message passing here. Merging is another important aspect of this work. The environments of conditional branches, the delta that you were seeing in the other slides, are conservatively merged here, and this enables us to maintain precision of our alias tracking. And the way we do this is by isolating, using the previous isolation technique that I described earlier, to take care of any values that go out of scope after you exit the branch. And we try to find a common annotation for all the remaining variables. But if we can't, again, it's conservative, we just mark it as inaccessible because we can't figure out what the aliasing is. This is, again, a limitation on the expressive power, but here again, we can assign precise blame whenever this fails. And by fail, I mean like it just marks it as inaccessible. As an example here, we might have a method that tries to do something like this. So in one branch, we instantiate a new node, and in another branch, we try to use the root node. But if we try to do this, we can't, because we have a unique value in the one branch and an alias in the other branch. There is no way to unify those annotations, and it results in it being inaccessible. But here again, we can precisely point, say, in this branch, it's this way, in this other branch, it's this way. Do something about it, I guess. And here we could, for example, do a destructive read, which fixes the problem because, yes, that's a problem I fixed in a later copy that apparently I did not copy here. But anyway, it's fixed because it's now unique in the other branch. Oh, wow. Okay, yeah. So our goals, recapping them. Sound reasoning. We think that this is sound. We were really excited about it at first because we were like, it's so simple. And then there's like edge cases. Wow, who would have thought? So, yeah, but we think it's sound now. We have yet to prove this. But we do have a formalism, and to our knowledge, it is sound. There are very few annotations. This is pretty easy. There's 3 of them. In fact, just 2 for fields. One is default. You don't even have to specify it. And local variable annotations are completely inferred. Again, this is because they can change during the lifetime. And we could use like tools and whatever to show this, which I'll get into later. But yeah, we do enforce simple invariants, at least we think it's simple to reason about. You have to reason about uniqueness on the heap. There's no separate graph of ownership or anything to reason about. We precisely track aliasing, as I was talking about earlier. And by precision, I mean we specifically identify an actual path that aliases this value, or that also references this value. And anything that we can't precisely track, we just say, you can't access it. It's not allowed. As I was saying before, this lets us do interesting things like precise blame whenever this fails, things like that, to help the user reason about some of the more complicated aspects. And I hope it's pretty clear that this definitely favors simplicity over expressiveness. Where we draw the line is up for debate here, but yeah. We do want to further evaluate this and see how expressive it is. We have some examples that from where we compared it to other work, and it seems relatively expressive for some definition, but we haven't evaluated it. So yeah. So yay, we did it. All right, we're all done. Except, well, there's a lot of questions about this. Is uniqueness alone expressive enough? That's a question. Maybe we can specify some unique core of objects and then use our liquid Java reasoning, like type state and etc., to reason about the structure of other values. But this is a question. Also, the usability, is this easier to understand than other approaches? We have yet to evaluate that. Should we allow temporarily breaking some of these invariants as long as we can show that they're restored? That's another question. It remains to be done to actually integrate this into tools, and we've done a lot of discussion on what the best way for this is. Do we want to encode the annotations in a separation logic and then pass that off to something else, or what should we do there? And developing IDE integrations. This is, I think, some interesting stuff here that is possible because we have this very precise alias tracking. We can highlight aliases, would be one example. We can do diagrams of the heap structure. We could precisely identify the source of some other errors that occur during verification, etc. So yeah, that is Latte. I'm Conrad again, and yes.
Okay.
I guess a little bit of shameless self-promotion. I am currently an undergrad going to grad school soon, so if you have any opportunities, I would be happy to talk to you.
Okay, so do we have questions?
Yeah, thank you very much. It's very interesting research. I was wondering, would you consider adding immutability as an additional parameter in your system? Because you could easily get around the issue of uniqueness, of separate uniqueness, by just making the system believe that objects are immutable as long as they are unique, as long as they're immutable.
Yeah. So that is one thing that we did discuss. We thought about it a little bit. It turns out that it's slightly more complicated to reason about than what you would initially want it to be. I'm forgetting exactly why right now, but yes, that is interesting. An interesting option that we should explore more, I think. Yeah.
If no one else, I have.
So you mentioned sound reasoning. What exactly do you mean? So data race freedom?
So, yes, I should have specified that. By sound, what I mean is that we actually do precise alias tracking. So if you modify an object, it should only affect the things that are aliased that we know are aliased and annotated as such. There's certain things, in our formalism we have a way judgment is determining the whole set of things that are aliased with an object, that sort of thing. So that's really what we're getting at, is that our aliasing is correct, or our aliasing analysis is correct, yeah.
And if I can add just one word to that, going back to one of Conrad's first slides, we intend for a client analysis of this to be liquid types for Java. Mm-hmm. So a verifier, of course, needs to know what the effects of an assignment are. And so it has to eventually be sound for that purpose.
Hey, this is really cool work. Have you worked out the interactions with Java's generic types yet? Does it stay simple? Well, I didn't see any examples with generic types, so that's why I'm asking.
Yeah, that's a good question. I think I think our current hypothesis is that yes, it stays simple. There is some questions about, do you want to allow polymorphism in the annotations? That would be something that we would need to work out. We do have subtyping. It seems to work as you would expect it to. Yeah, so I expect generics to work similarly, but yes, that's also remains to be done and shown that actually works.
Doc, I was wondering, you may have said this, but I may have missed it. If you have a method that takes a owned parameter, do you have to ensure that that doesn't escape from that method, so it gets returned to the caller? Or can I take a reference and return it, I guess is the question.
Right, it cannot escape from that method. It has to stay local, yeah.
So maybe that's one question to ask in your open questions in expressivity. That seems like a fairly common pattern, being able to get a reference to the contents of something that you call via a method call, which is what then, for example, Rust is lifetime tracking for. But yeah, thanks.
Yeah.
So with the topologies, we're only allowing unique pointers, you're going to be quite restricted in what you can do. So like your example where you had a queue, you looked like it was an O of n operation to do a DQ, whereas I would prefer it to be O of 1 and have 2 pointers to the tail. So do you have any thoughts on how you could be slightly more liberal in the uniqueness?
Yeah, so this is the really kind of maybe the big question that remains. I'm not sure. I mean, so the easy answer here is that we let things be shared, and then you can do whatever you want. And our hopes is that we can integrate that into Liquid Java in a way that nicely interacts with our uniqueness system, where we can specify more complex structures in the liquid types logic and save the overall heap structure, like the global invariants that we want in our uniqueness system, but that remains to be seen. Wait, could you clarify what you were saying about the stack?
So you had a DQ operation, but you traversed the entire stack to do the DQ, whereas if I were implementing a queue, I would have linear pointers effectively, but the last thing gets 2 pointers going to it because you have a tail pointer.
Right. That is one thing that, yes, we need to... it's unclear how you would do that in the current system. And so I would hope that we could have the tools to do that on the Liquid Java side to say that this is, we have a last value. But yeah.
Okay.
All right.
Seems that people were quite interested in this, so hopefully that will be a good omen for your graduate studies. Seems so to me. So we can then thank Conrad again.